Hello all, welcome back to my YouTube channel all about VLSI. In this particular video, let's try to discuss about MII interface, that is Media Independent Interface. So this is basically Ethernet protocol continuation, and in this particular series where we have discussed about introduction to OSI layer and TCP layer, and then we have moved to Ethernet frame structure, and we have discussed in detail about what are all the frames which we have in our Ethernet protocol. And then next we have moved with CRC calculation and what do you mean by CRC and how we are going to perform frame check sequence and all, and how we are going to perform serial CRC and parallel CRC and all we have discussed it. Now let's move to MII and let's try to discuss what do you mean by MII. Basically, this is what we are going to design. The MAC controller, this is what we are going to design. Let me highlight it so it will be clear. Yeah, so this is what we are going to design using our Verilog, right? Now, this will be written in Verilog, right? And this will be a physical IC or it is our physical Ethernet IC chip that we want that will be connected via Ethernet cable to the external device. From this cable, it will be connected to this particular IC, and from this IC, that the data should be transferred or received with our Verilog design or whatever the controller we are going to design. Okay. Now, what our design is going to do, it is going to control digital logic, and it is going to frame, and it is going to perform CRC, and it is going to perform addressing. Whereas what is the IC is going to do? IC is going to perform analog signal to voltages, and it is going to convert this analog signals to analog voltages to digital signals and all, and it will be converting and it will be given to our Mark design. Okay, so for connecting this particular Verilog design as well as our IC, we are going to use this MII interface. Now, so yeah, this is what I've told you. So when we send a data over an Ethernet cable, so the two different jobs needed to be happen. So these two jobs are so different that engineers decided to split them into two separate chips with a standard interface between them. That interface is nothing but MII, which stands for Media Independent Interface. Okay, so let's try to understand the scenario and why and where we are going to use this MIA and other possible options also. Now, so what is basically our Mac is doing? Let's try to understand. And let me open this pointer. One second. Let me open this pointer. Yeah. So basically, what is Mac going to do? Basically, this is what we are going to implement our Verilog code in our future sessions. Media access control, Mac controller IP we are going to design. So this controller IP is going to handle everything in the digital logics, and it is going to basically assemble Ethernet frames. That is, we have seen right in the previous sessions. We have seen that Ethernet frame is going to have preamble, SFD, DST, SRC, and type and data and CRC. So whatever the data which we are going to get from the upper layers or whatever the data which we are going to receive from the lower layers of our network layer, we are going to split them or we are going to join them accordingly, whether it is a transmitter or receiver, and who is going to do Ethernet controller is going to perform that. An Ethernet controller is going to perform CRC checking of a received frame is valid or not. It's going to basically receive a frame and it is going to perform CRC checking. And also there will be something known as interframe gap that also we are going to see, and it is also going to handle the flow control by pausing frames and all, and filtering the frames by MAC address. This is what a MAC controller is going to do, and this is what we are going to develop the code for, right? Now coming to my physical chip. So what is physical chip is going to do? It is going to convert the digital bits which the Mac is sending into electrical or optical signals according to the type of wire we are going to use, and converting incoming electrical signals into digital bags so that our Mac controller can use them. And auto negotiation, that means agreeing on speed or duplex with other side, and link detection, that is whether the cable is being detected or not, and speed and signal encoding. So this and all that physical chip is going to do. So if I want to connect this particular physical chip with my Mac, then I'm going to use something known as MII interface. Now, So this is how your MII interface is going to look like. So the word independent in MII means basically our mark design does not care whether the physical medium is a copper twisted pair or fiber optic or coaxial. You can see over here we can use any particular physical medium. It may be coaxial cable, or it may be fiber cable, or it may be copper cable. Your physical cable can be any physical chip may be connected to any particular interface. You whatever the code you're going to write can basically, if it want to communicate with any physical chip, we are going to use MII interface. That's the reason we are going to use the word over here independent. Okay. Yeah. So basically, we can swap the physical chip for a different medium, and our Mac Verilog code stays exactly the same. So this is the power of our separation. And basically, this MIA family is going to have different kind of extended interfaces. You might say, like this is what we are going to use in our Verilog coding. MIA interface we are going to develop, and the speed it can support is 10 to 100 megabits per second, and the width of the bus is basically 4 bits, which is nibble, and the clock frequency is 2.5 or 25 megahertz, right? And coming to other kind of interfaces are RMII, GMII, RGMII, and SGMMI. And as the interface goes on, the speed is also going to increase, and the bus width is accordingly, right? So these are the different kind of interfaces, and we are going to focus more upon MII interface in this particular course. Yeah, this is what I was saying about. So this will be our Ethernet MAC controller which will be present, and I'm going to have the MII interface which is present. And using this MII interface, I'm going to communicate with my physical chip, and this particular physical chip is going to basically connect to the external world using RJ45 Ethernet cables, and it is going to communicate it. So this is what we are going to design it. Now, in this particular MII interface, we are going to have two kind of buses. So one, and these are all MII interfaces buses, no, buses only. So MII is going to have two kind of buses. One is MII bus, and another is MDIO bus. So basically, this MII bus is used to transfer the data between our MAC controller and the physical chip. And this MDIO bus, MDIO basically is nothing but management interface, management interface. And using this MDIO bus, we are not going to send any actual data that we want to transmit or receive. If we want to transmit or receive the actual data, that will be transmitted or received using the MII bus, but not with MDIO bus. MDIO bus has a other special requirement that we are going to see in few seconds. But if you want to send or receive the actual data from your physical chip or to your physical chip from the Mac controller or to your Mac controller, we are going to use MII bus. Now, what are the signals which are present in our MII bus is first one is TXD, which is of 4 bits width, because we have seen, right, because it's basically is going to support one nibble. And next is TX underscore enable. So basically it is nothing but transmitter underscore enable. So this is my Mac controller, and this is my physical chip, and this physical chip is going to have TXT for transmission, and next is TX underscore enable. That means I'm going to enable this particular transaction for letting the physical chip know. And next is transmission error, that if there is any error in the transmission, this will come to know. And next is TX underscore clock. So clock we will be getting from the physical to Mac. This already we have discussed when we are discussing about preamp. And next is yeah, this is what the first set of signal is TX underscore clock. Basically, it is a transmission clock, and the direction is from physical to MAC, and the width is 1 bit, and frequency can be 25 megahertz, which supports 100 megabits per second, because 25 into data which we are going to send is 4 bits, right? So total data support is 100 megabits per second, or else 2.5 megahertz. That means 10 megabits per second. So this is we are going to decide accordingly. And yeah, this is what I was saying about. So this is a very important where our Mac is not going to generate any particular clock, or our Verilog code which we are going to develop is not going to generate any clock, but the physical chip is basically going to generate the clock using some crystal oscillators and all, and it is going to give that particular generated clock to our Mac. Next is TXT. TXT is basically the actual frame of data going out, and since the bus width is 4 and one full byte is sent using two clock cycles. If I want to send a byte of data, I'm going to use two cycles. Yeah, this is what I was saying about, and we will discuss this in more detail, like how we are going to transmit the data and receive the data. And next is TX underscore enable that I have shown you, right? And next is TX underscore error. So these are the different kind of uh, signals which are associated. So if I want to have a communication, then what I'm going to have is physical is going to provide me TX clock, then MAC is going to put the 4-bit data in onto my TXT, and MAC is going to assert this TX underscore enable is equal to 1, and every clock cycle next nibble is basically same, and after the frame is done, tx underscore enable is equal to 0. And how exactly we are going to use this tx underscore error, we will discuss in detail when we are going to implement this in our mac controller. And receiver side also same as TXT, we have RXT, RXDV. RXDV is nothing but data valid, that whatever the receiver is sending to the transmitter is a valid data, and RX and error like TX error, we have RX error, and RX clock is from physical to MAC, and CRS and COL. Basically, CRS is for carrier sense and COL is nothing but collision detection. This we will discuss in detail when we are going to design our MAC controller with MII interface. And yeah, this is what the detailed description where we have our code which is present, which is nothing but a media Mac present over here. And over here we have a TX clock which is being given by our physical, and RX clock is also given by our physical, which is basically recovered from incoming signals, right? Yes. And coming to next set of signals is management interface signals. And as I've told you previously that this particular signals are not used for basically sending you raw data information. Now, then why are these signals used for? Let us try to understand. So first of all, MDC stands for Management Data Clock and MDIO stands for Management Data Input Output. Now, we had a Mac which is present and we have a physical IC which is present. This is our Mac and this is our physical which is being connected to the external interface. Now, this particular physical is going to have some set of registers which is present inside this particular physical, and if I want to configure these registers, I am going to use this particular interface which is known as MDIO. MDIO is nothing but management data input output interface, which is basically going to access the registers which are present inside this physical and for configuring this particular physical registers. So this is where I can use this MDIO. Now, what are the registers which are present in this particular physical? I can think of basic control register like BMCR. Basically, the this particular register is most important and it basically controls the physical operation. And also basic status register. Basically, it is going to give the status of link, auto negotiation, physical capabilities, and etc. And next, physical identifier registers like whether it is physical ID1 or physical ID2. Like let's say suppose if I have a multiple ports which is present, then which particular port will be active, and what is a vendor and what is a model number. Like I have different kind of registers in this particular physical, right? So for configuring them or for knowing the values of this particular registers which are present inside this physical, I'm going to use this particular MDIO interface and I'm going to access those registers. So this is where I can think of. And MDC is again for data clock because I cannot simply configure this particular registers. I need to be having some kind of synchronization, right? So yeah, so this is about my MII interface. So with this particular knowledge, and let us try to develop a Verilog code, and I will also show you the what kind of architecture we are going to use and what are the different models we are going to have. Yes. Yeah. So that's about this particular session. If you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.